Let's consider the molar entropy of a gas. And in particular, we're going to use the methods of statistical mechanics, that is, the Sackur-Tetrode equation and partition functions, to calculate values of the molar entropy of an ideal gas. We're going to do two examples. One will be that of a monatomic gas. We'll use helium for that. And then we'll expand to a diatomic. So let's pose the question. Calculate the molar entropy of helium at standard pressure and a temperature of 298.15 Kelvin. And we're going to assume that helium is an ideal gas. We'll start with the Sackur-Tetrode equation, and we'll recognize that standard pressure, the word standard pressure means that we know the pressure. P naught, the standard pressure, is 1 bar, which is the same as 100,000 pascals or 100 kilopascals. The Sackur-Tetrode equation relates the entropy of n molecules to this logarithm, natural log. Kb, of course, is the Boltzmann constant, and then inside the natural log we have this ratio of the gas constant, temperature, Euler's number, raised to the 5½ powers, the thermal wavelength, we'll define that in a moment, Avogadro's number, and the pressure. So the standard molar entropy is obtained by taking the entropy. It's the standard entropy because it's referenced to the standard pressure down here. And we divide through by the number of moles, and that's how we get this SM naught value, right? Which is reference to the standard pressure, and then written here in terms of the thermal wavelength, which also brings in the dependence on the mass of a single molecule, lowercase m, mass of a single molecule. Let's substitute in all the other values we have for temperature, pressure. Again, the mass of a single molecule for helium will take the molar mass in kilograms, divide by Avogadro's number to get the mass of one molecule in SI units, kilograms. Substitute in all of those numbers, and what we'll find is we get a value of the molar entropy of helium at 298 Kelvin is equal to 126.2 joules per Kelvin per mole, which is exactly what the literature value is once we round off, right? The Sackur-Tetrode equation, which we have up here, and the thermal wavelength, they give us just the right answer for helium because it only has 1 degree of freedom. It has that translational degree of freedom with 3 components in it, X, Y, and Z. Let's go to the diatomic now, and CO. Let's take CO as our model diatomic molecule. If we again use the molar entropy calculated from the Sackur-Tetrode equation and the thermal wavelength, well, we could try that, right? Substituting temperature and pressure and the mass of a single molecule. When we make that calculation, we'd get a value of 150.4. Now, it's not a bad first approximation, about 24% off or so, but it's not exactly the same, right? The agreement's not as good as for helium. Why is that? That's because CO is a diatomic molecule that can rotate and vibrate. And we've got to take those degrees of freedom into account. All right, how can we do that? Let's go back to the definition of entropy in terms of the Helmholtz energy. Namely, if we take minus the partial derivative of Helmholtz energy with respect to temperature at constant volume, we'll get the entropy. Now let's express the Helmholtz energy in molar units. Again, we can use that with the relationship of moles to number of molecules and R to the Boltzmann constant, right? Go into the book, find that relationship for Helmholtz energy converted into molar units, and what we see is, oh wait, we've got to account for a couple of extra terms here. Now, we can forget about electronic excitation. We're not at very high temperature, 298 Kelvin, so we can forget about that. The first two terms here, that's exactly what comes from the Sackur-Tetrode equation, so we know the value that we put in there for those. But now we've got to deal with rotations and vibrations. And for that, we're going to have to calculate their partition functions and then take the log of those. So let's deal with these rotational and vibrational contributions. The rotational partition function, right, we're going to take an ideal rotor, a rigid rotor in the high temperature limit. Go to the book, look up the partition function for a rigid rotor at high temperature, and we find a very simple function, T over sigma theta r. Sigma is a symmetry number, 1 for a heteronuclear diatomic such as CO, and theta r, that's the rotational characteristic temperature, a very low number, 2.78 Kelvin for CO. What about the vibrational partition function? Well, the vibrational partition function, we know our ideal vibrator is the harmonic oscillator. And when we calculate the partition function, when we want to use that to calculate the entropy, we're going to set the zero of our energy as the zero of energy is the energy of the V equals 0 state. That is, we do not take into account 0-point energy for these thermodynamic calculations. The partition function will be defined here for a harmonic oscillator without 0-point energy, which converges on a nice value 1 over 1 minus the exponent of theta V over T. Theta V, the vibrational characteristic temperature, a very large number for CO. And we'll see the implications of that in just a moment. So now we have our expression for the molar entropy, standard molar entropy of a gas. We'll substitute in the standard pressure here, the rotational characteristic temperature here, the vibrational characteristic temperature there. We have values for all of those, and we get a much improved value. 198.3 joules per Kelvin per mole is within 4% of the correct answer. Note how the rigid rotor made a very large contribution. The harmonic oscillator made almost no contribution at all. Indeed, since the characteristic vibrational temperature is so high, there's very little population in V equals 1. We don't have to worry about the vibrational component very much. But with a very low rotational characteristic temperature, there is a large contribution from rotations. And indeed, the lack of agreement that we're finding here is from a breakdown in one of our assumptions. And the assumption that's really affecting things is that we've taken CO as a rigid rotor. A real rotor would have more states available to it than the rigid rotor does. And that last 4% to get from here to there, in order to get it even better, we'd need a better description of rotations. But we're doing pretty well, within 4% with the rigid rotor molecule. In summation, to calculate the molar entropy of a gas, we need to consider all available degrees of freedom, including translations for a monatomic. That's the whole story, and we can do that exactly, as well as rotations and vibrations for diatomic or polyatomic molecules. And to get exact answers, we'll need very good descriptions of those other degrees of freedom.